Hello again, good people. Now we have our example. I hope you enjoyed the first part of the video, which was talking about the history of calculus and where it all came from. So we have an example now. This gradient function actually means f prime at x. So don't listen to your teachers when they say you're calculating the gradient and you're using that. Okay. Don't tell them I said that. So calculate the gradient function from first principles of f at x equal to x raised to 2x squared. So now what happens? You know that you have your equation that we derived in the previous video of our gradient function, x plus h minus f at x, and this is all divided by h. So there some people actually they do this in different ways, but I'll actually show you a way that I find that is easier and that is quicker. So we all know if, for example, you have a function, maybe f at x is 2x plus 3, and then a question comes and say, okay, student, please find what is f at 2. F at 2, what do you do? Because they put the 2 in the x, you will also do the same. You put the 2 in the x, and then you simply just evaluate this, and it will give you 4 plus 3, and then it will give you 7. So that's what you also do here. But now you do it with respect to x, because they did not ask for a constant number, but now we are actually working with variables. So now, how do you start? You write this. You see this limit as h approaches 0. You always write it until you reach. I'll show you the step that you're supposed to reach, and then you can just drop it. Yeah? Bear in mind also, this h approaches 0 does not mean that h is equal to 0. Because if h is equal to 0, look at what's gonna happen. This whole thing will be undefined. It will be undefined. So now what do you do? So they took out the x and replaced it with x plus h. So you also do the same as a student who listens. You don't leave the square, because this is still the whole function. And then f at x is just this f at x. Ne? You are still with me. And then you have that. And then you have the limit as h approaches 0. Now we are just supposed to expand this binomial, and you know how to expand a binomial. I'm gonna tell you, I don't know if, but I'm sure you know this, but most what you do, you just open this into 2 brackets and then you use the FOIL method. We all know the FOIL method. A plus b, a plus b. FOIL method, you go a to a, go a to a, you go a to b, b to a, b to b. That's our FOIL method. And then, but I'm going to show you an easier way. What you do, you square this first one, you square it, and then that's for the first term. And then to find the second term, you multiply this, multiply x plus h, you take the sign, and then you times it by 2. So you say x plus h, and then you multiply it by 2. So you have something like that. And then now to find your third term, you just square your h, and there you have it. You've actually expanded your binomial in an easy way without opening 2 brackets. Okay, good. You are still seeing what's going on there. Still visible. What happens now? You still have this limit as h approaches our 0. Look at this now. X squared is going to cancel. It's going to cancel this x squared. And you'll be left with 2xh plus h squared, all divided by h. And then, as you can see, you can simplify this. We have an h here, we have an h there. H is going to 0. You take out the h, you're left with 2x plus h, all divided by h. And guys, h here will divide this h. It will not cancel it. It will divide it. Because I've always wanted to tell a larger group this. Because when you talk about something cancelling, you mean it's no longer there. And that is where you say x minus x, and then you get 0. The x's are no longer there. But now when you say x divided by x, there's still 1 here. We have 1, so x divides x here, and then here x cancels x. Yeah? Sorry to deviate. Let's proceed here. You still have the limit as h goes to 0. So now what happens here? What do you ask yourself? So the limit as h goes to 0. What happens when h goes to 0? It will disappear. Now h will be very small, that even adding 2x plus 2x on it, you still get something close to 2x. And then you'll have now that your answer is actually 2x. Thank you very much for that. Thank you for tuning in. I hope you understood what was going on. In my next video, I'll be doing an expansion of, I'll be doing an example of x cubed. So tune in for that. And I want to show you a trick there that's going to be very helpful. And then I'm also going to do one more example where our function actually has more than one more than one term. Thank you. Hello again. So here are the examples we are going to be doing now. F at x is equal to x cubed. F at x is equal to x squared plus 2x minus 3. And then we have this one. They say in your curriculum, this is a level 4 question. I don't know why, but yeah. So let's start with the first one. So for the first one, our f at x equal to x to the 3. We want to find our gradient function from first principles. I forgot to write that. From first principles. So we're finding our gradient function from first principles. We write the equation of our gradient, of finding our gradient equation, minus f at x all over h, and you have your limit h to the 0, same as we discussed in the previous example. You substitute the removed x and put in x plus h. The 3 is still there, minus f at x, which is just x to the 3, all divided by distance between these functions. Okay, so now this is a cubic difference of 2 cubes. Okay, so now I'm going to teach you all a way to actually do this. So some bit of a side note. I just don't want to waste your time. There's something called Pascal's triangle. Pascal's triangle actually helps you to expand anything you want to expand. But I'm going to show you for a cubic function, because that's what you're going to be doing. So let's say you have something like okay, let me just write this Pascal's triangle. I'm sure that you can see the pattern here. Pascal's triangle actually shows you coefficients that you will be needing. Coefficients that you will be needing, so on and so on, if you're to expand anything. If you're to expand anything. So for this one, if you have something like a plus b all raised to 0, it will be just 1, because anything raised to 0 is 1. And then if you were to take a plus b raised to 1, you have that this is a plus b. You have these coefficients 1 and 1. These coefficients 1 and 1 correspond with this coefficient. And then if you have a plus b all squared, what do you get here? You square the first one, a squared, you multiply this a times b, ab, take the sign, and you times by 2, and then you just square the last one. Can you see the pattern here? That's 1, that's the 1, this is the 2, and that's the 1. So now you can guess what will be a plus b to the 3. A plus b to the 3. You cube this one, yeah? Which means you're gonna have the first coefficient, and then you're gonna have a squared b plus 3 ab squared plus b cubed. You see, it gives you the coefficients. And then this middle part is actually easy, because you just interchange the 2. You see the 2's are here, and then you have 1's here. You first start with the square root of a, or you can do it either way around. It's going to be the same. That was just a side note. So when you expand this, you know now what it's going to be. A to the naught. So it's going to be x to the 3 plus, don't forget, 3 x h, 3x squared h plus 3x h squared plus h cubed minus x, and then this is all divided by h. And then you have your limit, h approaches 0. This x to the 3 will cancel that. You have 3x squared h plus 3x h squared plus h to the 3 all divided by h. And then you can just take the h out. You have 3x squared plus 3xh plus h squared all divided by h. This h will divide that h. And then we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared. So now when h goes to 0, this term will go to 0, and that term will go to 0, and then you'll be just left with 3x squared. Thank you guys. This was the first example.